Good day. In this lecture, we will be discussing redox reaction and voltaic cells, which are fundamental concepts in electrochemistry and engineering applications. By the end of this lecture, you should be able to define what a redox reaction is, interpret standard reduction potentials, and explain how galvanic or voltaic cells operate. Redox reaction involve the transfer of electrons. They are always coupled reaction, meaning that oxidation and reduction occur together. There is no oxidation without reduction, and there is no reduction without oxidation. To guide you, Leora means loss of electrons is oxidation, and the species is the reducing agent. Geroa means gain of electrons is reduction, and the species is the oxidizing agent. Electrochemical cells are devices that convert between chemical energy and electrical energy. There are two types, galvanic or voltaic cells, which generate electricity from spontaneous reactions, and electrolytic cells, which uses electricity to drive reactions. Our focus is on galvanic cells. In a galvanic cell, oxidation occurs at the anode. For example, copper metal loses electrons to form copper ions. Because electrons are produced, they accumulate at the anode, making it the negative electrode. These electrons move from the anode to the cathode through an external wire. And this movement of electrons is what produces an electric current. At the anode, reduction occurs. For example, silver ions gain electrons to form solid silver. The cathode is the positive electrode, and this follows Geroa. The driving force that moves electron is called the electromotive force, or cell potential E. It represents the tendency of a reaction to occur. Under standard condition, concentration is 1 molar, pressure is 1 atmosphere, and the temperature is 25 degrees Celsius. These values are listed in the standard reduction potential table. All half reactions in the table are written as reduction reactions. They are arranged from the strongest oxidizing agents to the strongest reducing agents. This table helps us predict the direction of your electron flow. If a metal like zinc acts as the anode, it undergoes oxidation. To use it with the table, we reverse the reaction, and when we reverse it, the sign of the potential. For the cathodes such as copper, the reaction is already written as reduction. So we use the value directly and the sign remains unchanged. Some important rules. If you reverse a reaction, the sign of the E changes. If you multiply reaction to balance electron, the value of E does not change. This is a common source of error, so be careful. A galvanic cell has an electrolyte where the anode is immersed, and a catholyte for the cathode, and a salt bridge as the internal circuit. The salt bridge maintains electrical neutrality in this environment. To maintain charge balance, anions move toward the anode and the cations move toward the cathode. This prevents charge buildup and allows the reaction to continue. In this example, copper is oxidized and silver ions are reduced. After balancing electrons, we calculate the cell potential. A positive E0 cell indicates that the reaction is spontaneous. To summarize, a galvanic cell converts chemical energy into electrical energy. The reaction is spontaneous and the E0 cell is positive. Oxidation occurs at the anode, which is negative, and reduction occurs at the cathode, which is positive. Electron flows from the anode into the cathode, and the anions move toward the anode. Meanwhile, the cations move toward the cathode. That concludes the lecture on redox reaction and voltaic cells. Make sure to practice using the standard reduction potential table as it is essential for solving problems.